Lesson: Predictive Maintenance and Resource Allocation using AI. Predictive maintenance and resource allocation using AI represent transformative approaches in the field of systems operations, offering significant advancements over traditional methodologies. Predictive maintenance aims to anticipate equipment failures before they occur, thereby maximizing uptime and minimizing costs. Meanwhile, AI-driven resource allocation ensures optimal use of resources, enhancing efficiency and productivity. Together, these technologies position organizations to tackle operational challenges proactively, leveraging data-driven insights to inform decision-making processes. Predictive maintenance harnesses the power of AI through advanced data analytics, machine learning, and sensor technologies. By continuously monitoring equipment and analyzing historical data, AI models can predict potential failures and schedule maintenance activities accordingly. For instance, a study by Lee et al. Demonstrates that predictive maintenance can reduce unplanned downtime by up to 50% and increase asset lifespan by 20 to 40%. These improvements translate into substantial cost savings and operational efficiency, making predictive maintenance an invaluable tool in SysOps. Implementing predictive maintenance begins with data collection. Sensors installed on machinery collect real-time data on various parameters such as temperature, vibration, and pressure. This data is then fed into AI algorithms, which use machine learning techniques to identify patterns and anomalies indicative of potential failures. Tools such as IBM's Watson IoT and Siemens MindSphere provide comprehensive platforms for integrating sensor data with AI analytics, enabling organizations to develop robust predictive maintenance strategies. Training machine learning models for predictive maintenance requires a substantial amount of historical data. However, the initial investment in data collection is offset by the long-term benefits of reduced maintenance costs and increased equipment reliability. For example, a case study involving a major European railway operator revealed that implementing predictive maintenance led to a 30% reduction in maintenance costs and a 25% increase in train availability. AI-driven resource allocation complements predictive maintenance by optimizing the use of resources, such as labor, materials, and energy. Machine learning algorithms assess historical and real-time data to forecast demand and allocate resources accordingly. This approach minimizes resource wastage and ensures that the right resources are available at the right time, enhancing operational efficiency. One practical tool for AI-driven resource allocation is Google's TensorFlow, an open-source machine learning framework that enables developers to build and deploy AI models efficiently. TensorFlow's flexibility and scalability make it ideal for developing resource allocation models tailored to specific organizational needs. Additionally, tools like Microsoft's Azure Machine Learning provide cloud-based platforms for building, training, and deploying AI models, facilitating seamless integration into existing systems. A compelling example of AI-driven resource allocation can be found in the energy sector, where AI models predict electricity demand and optimize power generation. By analyzing data on weather patterns, historical consumption, and grid conditions, AI systems can forecast demand with high accuracy, ensuring that power plants operate efficiently and sustainably. According to a report by the International Energy Agency, AI-driven resource allocation in the energy sector can reduce operational costs by up to 15% and decrease carbon emissions by 5 to 10%. The integration of predictive maintenance and AI-driven resource allocation requires a strategic approach, encompassing data management, model development, and system integration. Organizations must ensure that data is collected, stored, and processed efficiently, with robust data governance policies in place to maintain data quality and security. Furthermore, developing accurate and reliable AI models necessitates collaboration between data scientists, engineers, and domain experts, ensuring that models are tailored to specific operational requirements. A step-by-step approach to implementing predictive maintenance and resource allocation involves several key stages. Firstly, organizations must identify critical assets and resources that can benefit from AI-driven optimization. Next, data collection strategies should be established, leveraging sensors and IoT devices to gather relevant data continuously. Once sufficient data is collected, machine learning models can be developed and trained using frameworks like TensorFlow or Azure Machine Learning. Finally, the AI models must be integrated into existing systems with continuous monitoring and refinement to ensure optimal performance. Addressing real-world challenges in implementing these AI-driven strategies requires not only technical expertise, but also organizational change management. Establishing a culture that embraces data-driven decision-making is crucial, with training and support provided to staff at all levels. Moreover, organizations must be prepared to invest in the necessary infrastructure, such as cloud computing and data storage solutions, to support AI initiatives. The benefits of predictive maintenance and AI-driven resource allocation extend beyond cost savings and operational efficiency. These technologies also enhance safety by preventing equipment failures and optimizing resource usage, reducing the risk of accidents and environmental impact. In industries such as manufacturing, transportation, and energy, these benefits can lead to improved compliance with regulatory standards and enhanced corporate reputation. In conclusion, predictive maintenance and AI-driven resource allocation represent powerful tools in the SysOps domain, offering actionable insights and practical solutions to real-world challenges. By leveraging AI technologies, organizations can enhance operational efficiency, reduce costs, and improve safety, positioning themselves for long-term success. The integration of these strategies requires careful planning and execution, with a focus on data management, model development, and organizational change. As AI technologies continue to evolve, the potential for further advancements in predictive maintenance and resource allocation is immense, promising even greater benefits for organizations that embrace these innovative approaches.